There is an old saying about the 1849 California gold rush that gets thrown around Silicon Valley a lot. During a gold rush, the people who make the most reliable money aren't the ones digging for gold. The people who make the money are the ones selling the shovels and the blue jeans.
Levi Strauss didn't have to find a single nugget of gold to build an empire. He just had to supply the people who were convinced they were going to strike it rich. And when we look at the $2 trillion AI build-out we have been tracking, that exact same dynamic is playing out again.
Only this time, the gold is the AI compute, and the shovels aren't made of wood and iron. The modern shovels are made of highly specialized electrical steel, aluminum, and copper.
If you want to understand where the real friction is in the artificial intelligence supply chain right now, you have to stop looking at semiconductor fabs, and you have to start looking at heavy industrial metal foundries.
Quick, honest note before we dig in. This is just two curious people thinking out loud, for learning and for fun. It's not investment advice and never a buy or sell call, so always do your own homework. Welcome back to The Working Thesis. In our last episode, we talked about America's grid problem, how the country essentially needs to expand its transmission capacity by more than half, and how 2,300 gigawatts of power are stuck in a bureaucratic queue.
We established that moving the power from the plant to the data center is a massive hurdle. But today, we're going to look at the physical hardware of the grid itself. Because even if you get the permits, and even if you have the generation, you still have to physically control the electricity.
That requires heavy equipment. You cannot just take a high-voltage transmission line and plug it directly into a server rack. You will instantly melt the entire data center. You have to step that voltage down carefully and precisely until it is usable by a computer.
And the piece of equipment that does that is the hero of our story today. It is perhaps the most unglamorous, heavy, and critically constrained piece of technology on the planet right now. It is the humble power transformer.
To give you a sense of what a large power transformer actually is, forget everything you know about microelectronics. These are not printed on silicon wafers. These are massive, hulking steel boxes. A large power transformer can weigh hundreds of tons and is often the size of a small house.
They are the unsung sentinels of the modern world. Every time power is generated, it gets stepped up to an incredibly high voltage by a transformer, so it can travel long distances efficiently. And every time it reaches a city, or a factory, or a data center, another transformer steps that voltage back down.
Without them, the grid simply does not function. And because AI data centers require such immense, concentrated loads of electricity, they require highly specialized, incredibly robust transformers that can run near maximum capacity around the clock.
Which brings us to the core problem. The tech industry suddenly needs thousands of these massive units to satisfy its expansion plans. But the industrial supply chain that builds transformers was entirely unprepared for the AI boom.
The mismatch between tech demand and industrial supply has created a staggering bottleneck. As of recent industry surveys, the lead time for a large power transformer has ballooned to roughly 128 weeks.
And for the highly customized, top-tier units required for massive data center campuses, operators are being quoted lead times of up to 4 or even 5 years. You place the order today, and you might get your transformer delivered at the end of the decade.
Predictably, prices have skyrocketed. Analysts note that transformer prices are up roughly 60 to 80% from their historical baselines. It is a classic supply shock. The data center developers are practically begging for this equipment, bidding against utilities who just need to maintain the public grid.
If you are a hyperscaler trying to stand up an AI cluster to meet your contracted backlog, a 4-year wait for a transformer is completely unacceptable. But you can't just pay a software engineer to code one faster. It is a physical object that requires physical raw materials.
So why can't we just build more factories and crank these out faster? To understand the constraint, we have to open the box and look at how a transformer is actually built. It is essentially a feat of magnetic and electrical engineering.
Inside that massive steel tank, a transformer is primarily made of two things: a highly specialized metal core and thousands of pounds of conductive wire wound tightly around that core. The electricity flows through the wire, creating a magnetic field in the core, which then induces a different voltage in a second set of wires.
It sounds relatively simple in principle, but the physics dictate that the materials have to be absolutely perfect. If the metal core is inefficient, the transformer loses massive amounts of energy as heat.
And in an AI data center drawing hundreds of megawatts, even a tiny percentage drop in efficiency translates to millions of dollars in wasted electricity and massive overheating risks. So the manufacturers cannot compromise on the materials.
The absolute hardest material to source for these transformers is the metal for the core. It isn't just regular steel. It is a very specific, highly engineered product called grain-oriented electrical steel, or GOES for short.
GOES is the magic ingredient. Through a complex, tightly controlled rolling and heating process, the crystalline structure of the steel is aligned perfectly to conduct magnetic flux. It is incredibly difficult to manufacture at scale, and the global capacity to produce it is highly constrained.
In fact, the shortage of grain-oriented electrical steel is one of the primary reasons transformer lead times have stretched to 128 weeks. The transformer manufacturers simply cannot get enough of the core material to meet the orders coming in from the tech industry and the utility sector.
You can have all the copper wire and steel tanks in the world, but if you don't have GOES, you don't have a modern, high-efficiency power transformer. It is the ultimate choke point.
This brings up an incredible irony of the AI revolution. When people think of the companies enabling artificial intelligence, they think of the tech giants in Silicon Valley. But the most important company in the AI supply chain right now might just be making steel cores in the Rust Belt.
Exactly. Take the United States market as an example. The production of GOES is an incredibly niche industry. Currently, Cleveland-Cliffs is essentially the dominant primary domestic producer of this specific electrical steel in America.
They are an industrial mining and steel company operating blast furnaces and rolling mills. They don't write large language models, and they don't design neural networks. But without the highly specialized steel rolling off their lines, the AI data centers cannot get plugged into the grid.
It perfectly illustrates the selling shovels dynamic. The tech industry is pouring billions into AI, but a significant portion of that capital is inevitably flowing downstream into traditional, heavy industrial manufacturers who hold the keys to the physical infrastructure.
Beyond the steel cores, there's another material that gets a lot of attention in the grid narrative: copper. If you listen to mainstream commentary, you will often hear that the AI boom is going to require millions of miles of copper for new transmission lines.
We need to bust that myth right now. Yes, AI requires a lot of copper, but it isn't going into the massive high-voltage transmission lines stretching across the country. Those high-voltage lines, the ones you see strung between giant metal towers, are almost entirely made of aluminum.
Specifically, they are mostly ACSR, which stands for Aluminum Conductor Steel Reinforced. Aluminum is used for long-distance transmission because it is significantly lighter and cheaper than copper, while still offering excellent conductivity. The steel core simply provides the physical strength so the wire doesn't snap.
If we tried to string the national grid with copper, the towers would collapse under the weight, and the cost would bankrupt the country. So when we talk about expanding the national transmission grid, we are primarily talking about a massive demand shock for aluminum, not copper.
However, copper still plays a massive, critical role in the AI build-out. You just have to look closer to the end user. While aluminum handles the long-distance journey, copper is the undisputed king of local distribution and internal data center wiring.
Remember those massive power transformers we just talked about? The thousands of pounds of wire wound tightly around the GOES steel core? That is almost entirely high-grade copper.
And once the power enters the data center, it travels through copper bus bars, copper cables, and directly into the copper traces on the motherboards themselves. Copper is unmatched for handling high currents in tight, heat-sensitive spaces where weight isn't an issue.
So the AI materials thesis is split. Long-distance transmission drives aluminum demand, while the transformers, distribution gear, and the data centers themselves drive an insatiable appetite for copper.
It isn't just the raw materials that are in high demand. It is the finished grid gear and the companies that actually construct the infrastructure. The ecosystem of enablers is vast and deeply embedded in traditional engineering.
You have the companies manufacturing the switchgear, the circuit breakers, and the power management software. And then you have the engineering and construction firms, the builders who actually deploy the heavy machinery, pour the concrete footings, and string the aluminum lines across the mountains.
These are companies that have historically operated with slow, steady, single-digit growth tied to routine utility maintenance. Suddenly, they are being drafted into a frantic, multi-billion-dollar tech race, and their order books are overflowing.
For investors and industry watchers, these enablers offer a steadier, albeit less glamorous, perspective on the AI boom. They don't have to guess which foundational model will win or which AI startup will dominate the consumer market. They just know that whoever wins is going to need a circuit breaker.
But there is an important caveat to all of this. While the demand for transformers, steel, and grid gear is undeniably intense right now, these are historically highly cyclical industries.
Many of these industrial names are richly valued today because the market sees the AI backlog. But heavy manufacturing isn't software. When supply eventually catches up to demand, when the new steel mills and transformer factories finally come online, the pricing power can evaporate very quickly.
It is a reminder to look at where the value is currently flowing, without assuming it represents a permanent, uninterrupted upward trajectory. The shovel sellers are making incredible margins today, but predicting exactly when the infrastructure backlog clears is notoriously difficult.
The reality is that the physical world is messy. It takes time to mine the iron, refine the steel, wind the copper, and deliver a transformer. The tech industry is learning that it cannot simply code its way out of a commodities crunch.
Which leaves the hyperscalers and the neo-clouds in a very difficult position. They have $2 trillion in contracted demand, but they are being told to wait up to 4 years for the transformers and grid gear to power their facilities.
And in the tech sector, 4 years might as well be a century. They absolutely cannot wait. If the public grid and the traditional supply chain can't deliver the power fast enough, they have to find another way.
Next time on The Working Thesis, we look at the scramble. If you can't get permission to plug into the grid, what do? We're going to explore the massive, somewhat controversial pivot to behind-the-meter natural gas, flexible load agreements, and the brute force reality of bringing your own power plant to the data center.
The queue is blocked, so the tech industry is building its own bypass. We'll show you exactly how they are powering AI right now in episode 5. See you then.
That's a wrap for today. Thanks for thinking it through with us. We're just testing our theses out loud, one day at a time.
Catch you on the next one. Stay curious and tell us where we're wrong.